Welcome to Chapter 8, Quantities in Chemical Reactions, or Stoichiometry. And if you're wondering, what the heck is stoichiometry? Well, we're going to find out in this chapter, so stick around. So, in this chapter, we are going to think like a chef. Hopefully not this chef, if you're unfamiliar with this particular chef. I am so sorry. You've missed out on a great joy in life. The Swedish chef is the greatest chef alive. Just don't eat anything that he cooks. What I mean by we're thinking like a chef is that we're going to be thinking of chemical reactions very much like you think of a recipe. Because in reality, chemical reactions are very much like a recipe. So, for example, let's say you wanted to make some pancakes. And you have a recipe for pancakes that is very, very simple. Overly simple, probably, but just to keep things fairly simple here, not too complicated, we're going to go ahead and go with it. And the recipe says that if you mix 1 cup of flour, 2 eggs, and a ½ teaspoon of baking powder, and cook that, you will get, as a result, 5 pancakes. So those ingredients come together to give you 5 pancakes. Now that's pretty standard as far as recipes go. Like I said, it's maybe a little simplistic. You can definitely find pancake recipes out there with more than just 3 ingredients. But, it gets the point across. We have our flour, our eggs, and our baking powder, and those come together to make 5 pancakes. Now, thinking about this recipe, what if we had more than enough flour and baking powder, and we had 2 eggs? So we have more than enough of everything else, and we have 2 eggs. Well, according to the recipe, we can make 5 pancakes, because the recipe tells us that for every 2 eggs, we get, as a result, 5 pancakes. And again, this is assuming we have enough of everything else. So this gives us a ratio between the eggs and the pancakes. It's a 2 to 5 ratio. For every 2 eggs, you get 5 pancakes. So that is our ratio between the reactant, or ingredient in the case of cooking, and the product, or the pancakes, in this case, the actual food that we're making. So, what if we had 8 eggs? Again, assuming that we have more than enough of everything else. If we have 8 eggs, let me see, do we talk about this in the next one? No. Okay, so if we have 8 eggs, what we can do is we can use this ratio of 2 eggs for every 5 pancakes, and we can essentially use that ratio as a conversion factor. So we know that for every 2 eggs, we get 5 pancakes. And so if you do the math here, which I know some of you are thinking, well, why do we have to do the math? I mean, I can do that in my head. We can make, at the edge of the screen there. 8 divided by 2 is 4. 4 times 5 gives us 20 pancakes. So we can make 20 pancakes. Another way of thinking of this is just, we need 2 eggs for every 5 pancakes, and because we have 8 eggs, we can essentially get to those 2 eggs 4 times. But the math doesn't always work out quite so easy, and so I would suggest trying to use these ratios like this, because you don't have to worry about trying to do it in your head. So these ratios are everywhere in the recipe. So there is a ratio between the flour and the pancakes, and that's for every 1 cup of flour, you get 5 pancakes, and it's also there in the baking powder. For every ½ teaspoon of baking powder, you get 5 pancakes. And again, we're still having to assume that we have enough of everything else, but making that assumption, there are ratios between every recipe, or sorry, between every ingredient and the product, the pancakes. But not only that, there are recipes between the ingredients as well. So if you know how many cups of flour you have, you can work out how many teaspoons of baking powder you would need to use up that flour using the relationship between those two things. You're not limited to ratios with the product of the recipe. You can have a ratio between the ingredients as well. So for every 1 cup of flour, you would use up a half a teaspoon of baking powder. So with that in mind, if we had 5 cups of flour, how many teaspoons of baking soda would we need? Actually, that should say powder, sorry. Mixing up my ingredients, shame, shame. Baking soda and baking powder are not the same thing, although they do behave fairly similarly, but they are not the same thing. So baking powder here. How many pancakes could we make given that amount as well? So if we had 5 cups of flour, again, we're going to use this just like a conversion factor, the ratio between these two. We know that for every 1 cup of flour, we're going to need a half a teaspoon of the baking powder. And so that means we're going to need 2.5 teaspoons. And again, you probably could have done that math in your head, but like I said, it's not always going to be nice, simple math like this, so it's good to go ahead and get the practice in with the conversion process here with the easy stuff, instead of trying to figure it out with the harder stuff. And so then just taking that a step further, the next question there was how many pancakes can we make with that? Well, again, assuming we have more than enough of everything else, which in this case would be the eggs, if we have 5 cups of flour, we know that for every 1 cup of flour, we can make 5 pancakes, so that would give us 25 pancakes. And if you want to work that out with the ratios, you have 5 cups of flour, and you have, for every 1 cup, 5 pancakes. And so why did I put 1 there? 5. It's helpful if you write the correct thing. 5 pancakes. And so that ends up giving you 25 pancakes. So these ratios are everywhere in cooking. And it's the exact same process, the exact same thing that we are going to do now in chemistry. Because in chemistry, with our chemical reactions, we have ingredients and we have products that we make. And not only do we have ingredients and we have products, but the chemical reaction tells us how much of each of those things are going to react and be produced as well. So it's not just telling us you have hydrogen, nitrogen, and ammonia. It's telling us we have 3 hydrogens, 3 H2s, 1 N2, and that produces 2 ammonia. Or ammonia, sorry. So those ratios exist here in the chemical reactions as well. And we're going to take advantage of this in our stoichiometry. So moving on here, talking about using moles. So while the ratio is correct for individual molecules, it is practically impossible to work with just a few molecules. Instead, we work with moles of compounds and use the coefficients in front of the compounds to signify the number of moles of that compound. Remembering from the previous chapter when we talked about moles that a mole is just a number of things, it is perfectly fine to use moles as these numbers here. There's a 1 there that's not shown. As those numbers instead of the individual atoms or molecules. Now it's true that those ratios are for individual molecules and atoms, but we can expand that and think about them in terms of moles, and it still works perfectly fine. It's still the exact same thing. So from this point forward, When we talk about these coefficients, the numbers in front of the molecules, those are representing moles, not just molecules, not single molecules. All right. So, with the fact the ratios we're using are ratios of moles, let's go ahead and look at a practice problem here. So this is 8.1. Open that up in the book here. This says sodium chloride forms by this reaction between sodium and chlorine. So we have Na in the solid phase, and we have two of those. And that reacts with chlorine gas to form 2NaCl, which is a solid. So the question asks, how many moles of sodium chloride will result from the complete reaction of 3.4 moles of chloride? Or sorry, chlorine, not chloride. So if we have 3.4 moles of Cl2, how many moles of sodium chloride will we make? Assuming that we have enough chloride, assuming we have enough sodium. So if we have plenty of this, and we have 3.4 moles of this, how much of this can we make? So go ahead and pause the video, see if you can work that out on your own, and then come back and we'll work it through together. Alright, so what we're going to use here is the ratio between the two things that we're concerned with. The balanced chemical equation, and it does need to be balanced, it tells us that for every 1 mole of Cl2, we will make 2 moles of sodium chloride. So then, our moles of chlorine cancel out, leaving us with 6.8 moles of sodium chloride. So assuming we had more than enough of the sodium, and the 3.4 moles of chlorine reacted, we would make 6.8 moles of sodium chloride. Alright, we'll leave it there for this video. In the next one, we're going to take this idea one step further by including the masses. So not just converting from moles of one thing to moles of something else, but converting from the mass of something to the mass of something else. So we'll look at that in the next video.